Alright, welcome to a weekend video. This is going to be part for the class I'm doing with some friends in Austin. This is going to be the second to the last lesson for this. Next week will mark the end of this course. Personally, myself, I'm not going to choose to do another course on this, but I think the other participants in the course may decide to go and do another course which goes through the rest of the book. Myself, in going through and learning all this and stuff, just kind of doubts the value this would have for myself and my career. One thing I might be doing next, however, is the AI. So let's see here. So if I go to the JNCIESP folder, which is what I'm working towards right now, and then I log in, we can see that there's actually a AI track here, this MIST AI certification track. So I can get a free voucher and I can get this certification for free. So if there's any overlapping content on this, that's going to be okay. So that's going to be okay, so it's just the very first question. It looks like it's not at all related. It looks like, oh, okay, so this is probably better. This is the actual modules. Yeah, so this is like a PowerPoint on this topic. So, so it looks like this is going to be quite a bit different. There's really not going to be anything relating to AI specifically. It's more going to be Wi-Fi basics, WLAN basics. So this is more like a wireless certification, so we won't be learning about like weights and training models and all those sorts of things. Yeah, it's just we're learning about Marvis AI, but I'm not sure that this will overlap. Yeah, I'm not sure how much this will overlap with what I'm doing. And then one thing I do want to work through is the automation and DevOps certification. I have real-world experience in this, so it'd be nice to get a cert to go along with that. All right, so I'm going to be watching the video and then answering the questions. Before I start the video, I'll make a new folder for this new topic. Okay, and then a new Google Docs called the questions. Alright, so here are the questions. I want to make sure that they're correct. Sometimes this pane doesn't update. Alright, and let's see if we can get the first half an hour at least of this video watched. Set myself up for less to watch later in the day.
Hi, everybody.
And it's a 2-hour video, unfortunately, so I'll probably need to, I'm going to start with it at 1.5.
Everybody, and welcome to lesson 7. We're going to start by having a look at a kind of regularization called weight decay. And the issue that we came to at the end of the last lesson is that we were training our simple dot product model with bias, and our loss started going down, and then it started going up again. And so we have a problem that we are overfitting. And remember, in this case, we're using mean squared error. So try to recall why it is that we don't need a metric here, because mean squared error is pretty much the thing we care about, really. Or we could use mean absolute error if we like, but either of those works fine as a lot of fun. But they don't have the problem of big flat areas like accuracy does. So what we want to do is to make it less likely that we're going to overfit by doing something we call reducing the capacity of the model. The capacity of the model is basically how much space does it have to find answers. And if it can kind of find any answer anywhere, those answers can include basically memorizing the data set. So one way to handle this would be to decrease the number of latent factors. But generally speaking, reducing the number of parameters in a model, particularly as we look at more deep learning style models, ends up biasing the models towards very simple kind of shapes. But there's a better way to do it. Rather than reducing the number of parameters. Instead, we try to force the parameters to be smaller unless they're really required to be big. And the way we do that is with weight decay. Weight decay is also known as L2 regularization. They're very slightly different, but we can think of them as the same thing. And what we do is we change our loss function. And specifically, we change the loss function by adding to it the sum of all the weights squared. In fact, all the parameters squared, really should say. Why do we do that? Well, because if that's part of the loss function, then one way to decrease the loss would be to decrease the weights. One particular weight, or all of the weights, or something like that. And so when we decrease the weights, if you think about what that would do, then think about, for example, the different possible values of a in y equals ax squared. The larger a is, for example, a is 50, you get these very narrow peaks. In general, big coefficients are going to cause big swings, big changes in the loss, the small changes in the parameters. And when you have these kind of sharp peaks or valleys, it means that a small change to the parameter can make a small change to the input can make a big change to the loss. And so if you're in that situation, then you can basically fit all the data points close to exactly with a really complex, jagged function with sharp changes, which exactly tries to sit on each data point, rather than finding a nice smooth surface which connects them all together, or goes through them all. So if we limit our weights by adding in to the loss function the sum of the weights squared, then what it's going to do is it's going to fit less well on the training set because we're giving it less room to try anything that it wants to. But we're going to hope that it would result in a better loss on the validation set or the test set, so that it will generalize better. One way to think about this is that the loss with weight decay is just the loss plus the sum of the parameters squared times some number we pick, a hyperparameter. Sometimes it's like 0.1 or 0.01 or 0.001 kind of region. So this is basically what loss with weight decay looks like in this equation. But remember, when it actually comes to how is the loss used in stochastic gradient descent, it's used by taking its gradient. So what's the gradient of this? Well, if you remember back to when you first learned calculus, it's okay if you don't, the gradient of something squared is just 2 times that something. We changed from parameters to weight, which is a bit confusing. So just use weight here to keep it consistent. With your parameters is better. So the derivative of weight squared is just 2 times weight. So in other words, to add in this term to the gradient, we can just add to the gradient's weight decay times 2 times weight. And since weight decay is just a hyperparameter, we can just replace it with weight decay times 2. So that would just give us weight decay times weight. So weight decay refers to adding on to the gradients, the weights times some hyperparameter. And so that is going to try to create these kind of more shallow, less bumpy surfaces. So to do that, we can simply, when we call fit or fit one cycle or whatever, we can pass in a WD parameter, and that's just this number here. So if we pass in 0.1, then the training loss goes from 0.29 to 0.49, so it's much worse, right, because we can't overfit anymore. But the valid loss goes from 0.89 to 0.82, much better. So this is an important thing to remember for those of you that have done a lot of more traditional statistical models. Is in kind of more traditional statistical models, we try to avoid overfitting and we try to increase generalization by decreasing the number of parameters. But in a lot of modern machine learning, and certainly deep learning, we tend to instead use regularization, such as weight decay, because it gives us more flexibility. It lets us use more nonlinear functions and still reduces the capacity of the model. Great. So we're down to 0.823. This is a good model. This is really actually a very good model. And so let's dig into actually what's going on here, because in our architecture, remember, we basically just had 4 embedding layers. So what's an embedding layer? We've described it conceptually, but let's write our own. And remember, we said that an embedding layer is just a computational shortcut for doing a matrix multiplication by a one-hot encoded matrix, and that is actually the same as just indexing into an array. So an embedding is just a indexing into an array. And so it's nice to be able to create our own versions of things that exist in PyTorch and Fast AI, so let's do that for embedding. So if we're going to create our own kind of layer, which is pretty cool, we need to be aware of something, which is normally a layer is basically created by inheriting, as we've discussed, from a module or n.module. So for example, this is an example here of a module where we created a class called T that inherits from module, and when it's constructed, remember that's what dunder-init does, we're just going to set, this is just a dummy little module here, we're going to set self.a to the number 1 repeated 3 times as a tensor. Now, if you remember back to notebook 4, we talked about how the optimizers in PyTorch and Fast AI rely on being able to grab the parameters attribute, find a list of all the parameters. Now, if you want to be able to optimize self.a, you would need it to appear in parameters, but actually, there's nothing there. Why is that? That's because PyTorch does not assume that everything that's in a module is something that needs to be learned. To tell it that it's something that needs to be learned, you have to wrap it with nn.parameter. So here's exactly the same class, but torch.ones, which is just a list of three ones, in this case, is wrapped in nn.parameter, and now if I go parameters, I see I have a parameter with 3 ones in it. And that's going to automatically call requires grad underscore for us as well. We haven't had to do that with things like nn.linear in the past, because PyTorch automatically uses nn.parameter internally. So if we have a look at the parameters for something that uses nn.linear with no bias layer, you'll see again we have here a parameter with 3 things in it. So we want to, in general, be able to create a parameter, so something with a tensor with a bunch of things in, and generally we want to randomly initialize them. So randomly initialize, we can pass in the size we want, we can initialize a tensor of zeros of that size, and then randomly generate some normally distributed random numbers with a mean of 0, standard deviation of 0.01, no particular reason I'm picking those numbers, just show how this works. So here's something that will give us back a set of parameters of any size we want. And so now we're going to replace, everywhere that used to say embedding, I'm going to replace it with create params. Everything else here is the same in the init, under init. And then the forward is very, very similar to before. As you can see, I'm grabbing the 0 index column from X, that's my users, and I just look it up, as you see, in that user factors array. And the cool thing is I don't have to do anything with gradients myself for this manual embedding layer, because PyTorch can figure out the gradients automatically, as we've discussed. So then I've just got the dot product as before, add on the bias as before, do the sigmoid range as before. And so here's a dot product bias without any special PyTorch layers, and we fit, and we get the same result. So I think that is pretty amazingly cool. We've really shown that the embedding layer is nothing fancy, it's nothing magic, right? It's just indexing into an array. So hopefully that removes a bit of the mystery for you. So let's have a look at this model that we've created and we've trained and find out what it's learned. It's already useful, we've got something we can make pretty accurate predictions with. But let's find out what the model looks like. So remember when we create...
have a question.
Okay, let's take a question before you can look at this.
What's the advantage of creating our own embedding layer over the stock PyTorch one?
Oh, nothing at all. We're just showing that we can. It's great to be able to dig under the surface, because at some point you'll want to try doing new things. So a good way to learn to do new things is to be able to replicate things that already exist, and you understand how they work. It's also a great way to understand the foundations of what's going on, is to actually create in code your own implementation. But I wouldn't expect you to use this implementation in practice. But basically it removes all the mystery. So if you remember, we created a learner called learn, and to get to the model that's inside it, you can always call learn.model. And then inside that, there's going to be automatically created for it, sorry, not automatically, we've created all these attributes, movie factors, movie bias, and so forth. So we can grab learn.model.movieBias. And now what I'm going to do is I'm going to sort that vector, and I'm going to print out the first 5 titles. And so what this is going to do is it's going to print out the movies with the smallest bias. And here they are. What does this mean? Well, it kind of means these are the 5 movies that people really didn't like. But it's more than that. It's not only do people not like them, but if we take account of the genre they're in, the actors they have, whatever the latent factors are, people like them a lot less than they expected. So maybe, for example, this is kind of, I haven't seen any of these movies, luckily, but perhaps this is a sci-fi movie, so people who kind of like these sci-fi movies found this so bad that people didn't like it. So we can do the exact opposite, which is to sort ascending, and here are the top 5 movies, and specifically they're the top 5 by bias, right? So these are the movies that even after taking account of the fact that
I haven't seen LA Confidential. I kind of want to watch it now that it's in this list.
Because I would agree that these are all like pretty good. Like, I don't know, like Titanic was a bit like cheesy for me. Well, it was good when it came out. I'd say I like Titanic, but it's just not my favorite kind of genre. Shawshank Redemption was really good. Star Wars is really good, although I like the second one better. Oops.
Confidential, I have seen all of these ones. So LA Confidential is a kind of a murder mystery cop movie, I guess. And people who don't necessarily like that genre, or I think Guy Pearce was in it, so maybe they don't like Guy Pearce very much, whatever, people still like this movie more than they expect. So this is a kind of a nice thing that we can look inside our model and see what it's like. We can look at not only at the bias vector, but we can also look at the factors. Now, there are 50 factors, which is too many to visualize. So we can use a technique called PCA, Principal Components Analysis. The details don't matter, but basically they're going to squish those 50 factors down to 3. And then we'll plot the top 2, as you can see here. And what we see when we plot the top 2 is we can kind of see that the movies have been kind of spread out across a space of some kind of latent factors. And so if you look at the far right, there's a whole bunch of kind of big budget action-y things. And on the far left, there's more like cult kind of things, Fargo, Schindler's List, Monty Python. By the same token, at the bottom, we've got some English Patient, Harry Met Sally, so kind of romance, drama kind of stuff. And at the top, we've got action and sci-fi kind of stuff. So you can see, even though we haven't passed in any information about these movies, all we've seen is who likes what. These latent factors have automatically kind of figured out a space or a way of thinking about these movies based on what kinds of movies people like and what other kinds of movies they like along with those. So that's really interesting to kind of try and visualize what's going on inside your model. Now, we don't have to do all this manually. We can actually just say, give me a collab learner using this set of data loaders with this number of factors and this Y range, and it does everything we just seen. Again, about the same number. Okay? So now you can see, this is nice, right? We've actually been able to see right underneath inside the collab learner part of the FastAI application, the collaborative filtering application, and we can build it all ourselves from scratch. We know how to create the SGD, know how to create the embedding layer, we know how to create the model, the architecture. So now you can see, we really can build up from scratch our own version of this. So if we just type learn.model, you can see here, the names are a bit more generic. This is a user weight, item weight, user bias, item bias, but it's basically the same stuff we've seen before. And we can replicate the exact analyses we saw before by using this same idea. Okay? Slightly different order this time because it's a bit random, but pretty similar as well. Another interesting thing we can do is we can think about the distance between two movies. So let's grab all the movie factors, or let's pop them into a variable, and then let's pick some movie, and then let's find the distance from that movie to every other movie. And so one way of thinking about distance is, you might recall the Pythagorean formula, or the distance on the hypotenuse of a triangle, which is also the distance to a point in a Cartesian plane on a chart, which is root x squared plus y squared. You might know, doesn't matter if you don't, but you can do exactly the same thing for 50 dimensions. It doesn't just work for 2 dimensions. So that tells you how far away a point is from another point, if x and y are actually differences between two movie vectors. So then what gets interesting is you can actually then divide that kind of by the length to make all the lengths the same distance to find out how the angle between any two movies. And that actually turns out to be a really good way to compare the similarity of two things. That's called cosine similarity. And so the details don't matter. You can look them up if you're interested. But the basic idea here is to see that we can actually pick a movie and find the movie that is the most similar to it based on these factors. Kind of interesting.
I have a question.
All right.
What motivated learning at a 50-dimensional embedding and then using PA to reduce to 3 versus just learning a 3-dimensional?
Oh, because the purpose of this was actually to create a good model. So the visualization part is normally kind of the exploration of what's going on in your model, and so with 50 latent factors, you're going to get a more accurate. So that's one approach, is this dot product version. There's another version we could use, which is we could create a set of user factors and a set of item factors, and just like before, we could look them up. But what we could then do, instead of doing a dot product, we could concatenate them together into a tensor that contains both the user and the movie factors next to each other. And then we can pass them through a simple little neural network. Linear, ReLU, linear, and then sigmoid range as before. So importantly here, the first linear layer, the number of inputs is equal to the number of user factors plus the number of item factors. and the number of outputs is however many activations we have. And then we just default to 100 here, and then the final layer will go from 100 to 1 because we're just making one prediction. And so we could create, we'll call that collab NN. We can instantiate that to create a model. We can create a learner, and we can get. It's not going quite as well as before. It's not terrible, but it's not quite as good as our .product version. But the interesting thing here is it does give us some more flexibility, which is that since we're not doing a .product, we can actually have a different embedding size for each of users versus items. And actually, FastAI has a simple heuristic. If you call get embedding size and pass in your data loaders, it will suggest appropriate size embedding matrices for each of your categorical variables. Okay, so each of your user and item tensors. So that's so if we pass in star m's embeddings, that's going to pass in the user tuple and the item tuple, which we can then pass to embedding. This is the star prefix we learned about in the last class. So this is kind of interesting. We can, we can see here that there's two different architectures we could pick from. It wouldn't be necessarily obvious ahead of time which one's going to work better. In this particular case, the simplest one, the .product one, actually turned out to work a bit better, which is interesting. This particular version here, if you call collab learner and pass useNN equals true, then what that's going to do is it's going to use this version, the version with the concatenation and the linear layers. So collab learner, useNN equals true, again we get about the same result as we expect because it's just a shortcut for this version. And it's interesting actually, we have a look at collab learner, it actually returns an object of type embedding NN. And it's kind of cool, if you look inside the FastAI source code, we'll use the double question mark trick to see the source code for embedding NN, you'll see it's 3 lines of code. How does that happen? Because we're using this thing called tabular model, which we will learn about in a moment. But basically this neural net version of collaborative filtering is literally just a tabular model in which we pass no continuous variables and some embedding sizes. So we'll see that in a moment. Okay, so that is collaborative filtering. And again, take a look at the further research section in particular after you finish the questionnaire, because there's some really important next steps you can take to push your knowledge and your skills. So let's now move to Notebook 9, tabular. And we're going to look at tabular modeling and do a deep dive. And let's start by talking about this idea that we were starting to see here, which is embeddings. And specifically, let's move beyond just having embeddings for users and items, but embeddings for any kind of categorical variable. So really, because we know an embedding is just a lookup into an array, it can handle any kind of discrete categorical data. So things like age are not discrete, they're continuous numerical data, but something like sex or postcode are categorical variables. They have a certain number of discrete levels. The number of discrete levels they have is called their cardinality. So to have a look at an example of a data set that contains both categorical and continuous variables, we're going to look at the Rossmann sales competition that ran on Kaggle a few years ago. And so basically what's going to happen is we're going to see a table that contains information about various stores in Germany, and the goal will be to try and predict how many sales there's going to be for each day in a couple of week period for each store. So one of the interesting things about this competition is that one of the gold medalists used deep learning, and it was one of the earliest known examples of a state-of-the-art deep learning tabular model. I mean, this is not long ago, 2015 or something, but really this idea of creating state-of-the-art tabular models with deep learning has not been very common, and for not very long. Interestingly, compared to the other gold medalists in this competition, the folks that used deep learning used a lot less feature engineering and a lot less domain expertise. And so they wrote a paper called Entity Embeddings of Categorical Variables, in which they basically described the exact thing that you saw in Notebook 8, the way you can think of one-hot encodings as just being embeddings, you can concatenate them together, and you can put them through a couple of layers, they call them dense layers, we call them linear layers, and create a neural network out of that. So this is really a neat, kind of simple and obvious in hindsight trick. And they actually did exactly what we did in the paper, which is to look at the results of the trained embeddings. And so, for example, they had an embedding matrix for regions in Germany. Because there wasn't really metadata about this. These were just learned embeddings, just like we learned embeddings about movies. And so then they just created, just like we did before, a chart where they popped each region according to, I think, probably a PCA of their embeddings. And then if you circle the ones that are close to each other in blue, you'll see that they're actually close to each other in Germany. And ditto for red, and ditto for green, and then here's the brown. So this is like pretty amazing, is the way that we can see that it's kind of learned something about what Germany looks like, based entirely on the purchasing behavior of people in those states. Something else they did was to look at every store, and they looked at the distance between stores in practice, like how many kilometers away they are. And then they looked at the distance between stores in terms of their embedding distance, just like we saw in the previous notebook. And there was this very strong correlation that stores that were close to each other physically ended up having close embeddings as well, even though the actual location of these stores in physical space was not part of the model. Ditto with days of the week, so the days of the week were another embedding, and the days of the week that were next to each other ended up next to each other in embedding space, and ditto for months of the year. So pretty fascinating the way kind of information about the world ends up captured just by looking at gradient embeddings, which, as we know, are just index lookups into an array. So the way we then combine these categorical variables with these embeddings with continuous variables, what was done in both the entity embedding paper that we just looked at, and then also described in more detail by Google when they describe how their recommendation system in Google Play works. This is from Google's paper, is they have the categorical features that go through the embeddings, and then there are continuous features, and then all the embedding results and the continuous features are just concatenated together into this big concatenated table that then goes through, in this case, 3 layers of a neural net. And interestingly, they also take the collaborative filtering bit and do the dot product as well and combine the two. So they use both of the tricks we used in the previous notebook and combine them together. So that's the basic idea we're going to be seeing for moving beyond just collaborative filtering, which is just 2 categorical variables, to as many categorical and as many continuous variables as we like. But before we do that, let's take a step back and think about other approaches. Because as I mentioned, the idea of deep learning as a kind of a best practice for tabular data is still pretty new, and it's still kind of controversial. It's certainly not always the case that it's the best approach. So when we're not using deep learning, what would we be using? Well, what we'd probably be using is something called an ensemble of decision trees. And the 2 most popular are random forests and gradient boosting machines or something similar. So basically, between multi-layered neural networks like with SGD and ensembles of decision trees, that kind of covers the vast majority of approaches that you're likely to see for tabular data. And so we're going to make sure we cover them both, of course, today, in fact. So although deep learning is nearly always clearly superior for stuff like images and audio and natural language text, these 2 approaches tend to give somewhat similar results a lot of the time for tabular data. So let's take a look. You really should generally try both and see which works best for you for each problem you look at.
Why does the range go from 0 to 5.5 if the maximum is 5?
That's a great question. The reason is, if you think about it for sigmoid, it's actually impossible for a sigmoid to get all the way to the top or all the way to the bottom. Those are asymptotes. So no matter how big your x is, it can never quite get to the top, or no matter how small it is, it can never quite get. So if you want to be able to actually predict a rating of 5, then you need to use something higher than 5 for your maximum.
Are embeddings used only for highly cardinal categorical variables, or is this approach used in general? For low cardinality, one use one-hot encoding.
So I'll remind you, cardinality is the number of discrete levels of variable. And remember that an embedding is just a computational shortcut for a one-hot encoding. So there's really no reason to use a one-hot encoding, because it's as long as you have more than 2 levels, it's always going to be more memory and slower and give you exactly mathematically the same thing. And if there's just 2 levels, then it is basically identical. So there isn't really any reason not to use it. Thank you for those great questions. Okay.
All right, so I'm going to take a break. My goal was to get to the half-an-hour mark, so I made it. So when I come back, I'll try to get to the hour mark. Okay, welcome back. I took a break, so I'm going to see if I can get to the hour mark.
So one of the most important things about decision tree ensembles is that at the current state of the technology, they do provide faster and easier ways of interpreting. I think that's rapidly improving for deep learning models on tabular data, but that's where we are right now. They also require less hyperparameter tuning, so they're easier to kind of get right the first time. So my first approach for analyzing a tabular data set is always an ensemble of decision trees. And specifically, I pretty much always start with a random forest, because it's just so reliable. Yes?
Your experience for highly imbalanced data, such as fraud or medical data, what you should best out of random forest, XGBoost, or neural network?
I'm not sure that whether the data is balanced or unbalanced is a key reason for choosing one of those over the others. I would try all of them and see which works best. So the exception to the guideline about start with decision tree ensembles as your first thing to try would be if there's some very high cardinality categorical variables, then they can be a bit difficult to get to work really well in decision tree ensembles. Or if there's something like, most importantly, if it's like plain text data or image data or audio data or something like that, then you definitely going to need to use a neural net in there, but you could actually ensemble it with a random forest, as we'll see. Okay, so clearly we're going to need to understand how decision tree ensembles work. So PyTorch isn't a great choice for decision tree ensembles. They're really designed for gradient-based methods, and random forests and decision tree growing are not really gradient-based methods in the same way. So instead we're going to use a library called scikit-learn, referred to as sklearn as a module. Scikit-learn does a lot of things. We're only going to touch on a tiny piece of them, stuff we need to do to train decision trees and random forests. We've already mentioned before Wes McKinney's book, also a great book for understanding more about scikit-learn. So the data set for learning about decision tree ensembles is going to be another data set. It's called the Blue Book for Bulldozers data set, and it's a Kaggle competition. So Kaggle competitions are fantastic. They are machine learning competitions where you get interesting data sets, you get feedback on whether your approach is any good or not. You can see on a leaderboard what approaches are working best, and then you can read blog posts from the winning contestants sharing tips and tricks. It's certainly not a substitute for actual practice doing end-to-end data science projects, but for becoming good at creating predictive models that are predictive, it's a really fantastic resource, highly recommended. And you can also submit to most old competitions to see how you would have gone without having to worry about the kind of stress of like whether people will be looking at your results because they're not publicized or published if you do that. Yes?
There's a question.
Sure.
Can you comment on real-time applications of random forest? In my experience, they tend to be too slow for real-time use cases like a recommender system. Neural network is much faster when run on the right hardware.
Well, let's get to that and what they are, shall we? Now, you can't just download and untar Kaggle datasets using the untar data thing that we have in FastAI, so you actually have to sign up to Kaggle and then follow these instructions for how to download data from Kaggle. Make sure you replace creds here with what it describes. You need to get a special API code and then run this one time to put that up on your server. And now you can use Kaggle to download data using the API. So after we do that, we're going to end up with a bunch of, as you see, CSV files. So let's take a look at this data. So the main table is train.csv. Remember, that's comma-separated values. And the training set contains information such as unique identifier of a sale, unique identifier of a machine, sale price, sale date. So what's going on here is one row of the data represents a sale of a single piece of heavy machinery, like a bulldozer, at an auction. So it happens at a date, has a price, it's of some particular piece of equipment, and so forth. So if we use pandas again to read in the CSV file, let's combine training and value together. We can then look at the columns to see there's a lot of columns there, and many things which I don't know what the hell they mean, like blade extension and pad type and ride control. But the good news is we're going to show you a way that you don't have to look at every single column and understand what they mean, and random forests are going to help us with that as well. So once again, you're going to be seeing this idea that models can actually help us with data understanding and data cleanup. One thing we can look at is ordinal columns, a good place to look at that now. If there's things there that you know are discrete values but have some order, like product size, it has medium and small and large, medium and mini, these should not be in alphabetical order or some random order. They should be in this specific order, right? They have a specific ordering. So we can use as type to turn it into a categorical variable, and then we can say set categories ordered equals true, to basically say this is an ordinal column. So it's got discrete values, but we actually want to define what the order of the classes are. We need to choose which is a dependent variable, and we do that by looking on Kaggle. And Kaggle will tell us that the thing we're meant to be predicting is sale price. And actually, specifically, they'll tell us the thing we're meant to be predicting is the log of sale price, because root mean squared log error is what we're actually going to be judged on in the competition. So we take the log. So we're going to replace sale price with its log, and that's what we'll be using from now on. So a decision tree ensemble requires decision trees. So let's start by looking at decision trees. So a decision tree, in this case, is something that asks a series of binary, that is yes or no questions about data. So such as, is somebody less than or greater than less than 30? Yes, they are. Are they eating healthily? Yes, they are. And so, okay, then we're going to say they're fit or unfit. So like, here's an example of some arbitrary decision tree that somebody might have come up with. It's a series of binary yes and no choices, and at the bottom are leaf nodes that make some prediction. Now, of course, for our bulldozers competition, we don't know what binary questions to ask about these things and in what order in order to make a prediction about sale price. So we're doing machine learning, so we're going to try and come up with some automated way to create the questions. And there's actually a really simple procedure for doing that. You have to think about it. So if you want to kind of stretch yourself here, have a think about what's an automatic procedure that you can come up with that would automatically build a decision tree where the final answer would do a significantly better than random job of estimating the sale price of one of these options. Right, so here's the approach that we could use. Loop through each column of the data set. So we're going to go through each of, well, obviously not sale price, that's the dependent variable, sale ID, machine ID, auctioneer, year made, etc. And so one of those will be, for example, product size. And so then what we're going to do is we're going to loop through each possible value of product size, large, medium, etc. And then we're going to do a split, basically like where this comment is. And we're going to say, okay, let's get all of the options of large equipment and put that into one group, and everything that's smaller than that and put that into another group. And so that's here, split the data into two groups. based on whether they're greater than or less than that value. If it's a categorical non-ordinal value, a variable, it'll be just whether it's equal or not equal to that level. And then we're going to find the average sale price for each of the two groups. So for the large group, what was the average sale price? For the smaller than large group, what was the average sale price? And that will be our model. Our prediction will simply be the average sale price for that group. And so then you can say, well, how good is that model? If our model was just to ask a single question with a yes-no answer, put things into two groups, and take the average of the group as being our prediction, then we can say, how good would that model be? What would be the root mean squared error from that model? And so we can then say, all right, how good would it be if we use large as a split? And then let's try again. What if we did large/medium as a split? What if we did medium as a split? And so in each case, we can find the root mean squared error of that incredibly simple model. And then once we've found that for all of the product size levels, we can go to the next column and look at usage band, and do every level of usage band, and then state, every level of state, and so forth.
Oops, I'm hearing some noise outside. I might need to put on my headphones.
And so there'll be some variable and some split level which gives the best root mean squared error of this really, really simple model. And so then we'll say, okay, that would be our first binary decision. It gives us two groups, and then we're going to take each one of those groups separately and find another single binary decision for each of those two groups using exactly the same procedure. So then we'll have four groups. And then we'll do exactly the same thing again separately for each of those four groups, and so forth. So let's see what that looks like. And in fact, once we've gone through this, you might even want to see if you can implement this algorithm yourself. It's not trivial, but it doesn't require any special coding skills, so hopefully you can find you'll be able to do it. There's a few things we have to do before we can actually create a decision tree in terms of just some basic data munging. One is, if we're going to take advantage of dates, we actually want to call FastAI's add date part function. And what that does, as you see, after we call it, is it creates a bunch of different bits of metadata from that data. Sale year, sale month, sale week, sale day, and so forth. So sale date of itself doesn't have a whole lot of information directly, but we can pull lots of different information out of it. And so this is an example of something called feature engineering, which is where we take some piece of data and we try to create lots of other pieces of data from it. So is this particular date the end of a month or not? Is it the end of a year or not? And so forth. So that handles dates. There's a bit more cleaning we want to do, and FastAI provides some things to make cleaning easier. We can use the tabular pandas class to create a tabular data set with pandas. And specifically, we're going to use two tabular processors, or tabular procs. A tabular processor is basically just a transform, and we've seen transforms before, so go back and remind yourself what a transform is. Except it's slightly different. It's like 3 lines of code, if you look at the code for it. It's actually going to modify the object in place, rather than creating a new object and giving it back to you. And that's because often these tables of data are kind of really big, and we don't want to waste lots of RAM. And it's just going to run the transform once and save the result, rather than doing it lazily when you access it. For the same reason, we just try to make this a lot faster. So you can just think of them as transforms, really. So one of them is called Categorify, and Categorify is going to replace a column with numeric categories, using the same basic idea of like a vocab, like we've seen before. Fill missing is going to find any columns with missing data, and it's going to fill in the missing data with the median of the data, and create a new column, new Boolean column, which is set to true for anything that was missing. So these two things are basically enough to get you to a point where most of the time you'll be able to train a model. Now, the next thing we need to do is think about our validation set. As we discussed in lesson 1, a random validation set is not always appropriate. And certainly for something like predicting auction results, it almost certainly is not appropriate, because we're going to be wanting to use a model in the future, not at some random date in the past. So the way this Kaggle competition was set up was that the test set, the thing that you had to fill in and submit for the competition, was 2 weeks of data that was after any of the training set. So we should do the same thing for a validation set. We should create something which is where the validation set is the last couple of weeks of data. And so then the training set will only be data before that. So we basically can do that by grabbing everything before October 2011, create our training and validation set based on that condition, and grabbing those bits. So that's going to split our training set and validation set by date, not randomly. We're also going to need to tell, when you create a tabular pandas object, you're going to be passing in a data frame, you're going to be passing in your tabular procs, and you also have to say, what are my categorical and continuous variables? We can use FastAI's cat split to automatically split the data frame to continuous and categorical variables for you. So we can just pass those in. Tell it what is a dependent variable, you can have more than one, and what are the indexes to split into training and valid. And this is a tabular object. So it's got all the information you need about the training set, the validation set, categorical and continuous variables, and the dependent variable, and any processes to run. It looks a lot like a datasets object, but it has a .train, it has a .valid, and so if we have a look at .show, we can see the data. But .show is going to show us the string data, but if we look at .items, you can see internally it's actually stored these very compact numbers, which we can use directly in a model. So FastAI has basically got us to a point here where we have our data into a format ready for modeling, and our validation set's being created. To see how these numbers relate to these strings, we can, again, just like we saw last week, use the classes attribute, which is a dictionary that basically tells us the vocab. So this is how we look up, for example, 6 is 0, 1, 2, 3, 4, 5, 6. This is a compact example. That processing takes a little while to run, so you can go ahead and save the tabular object, and so then you can load it back later without having to rerun all the processing. So that's a nice kind of fast way to quickly get back up and running without having to reprocess your data. So we've done the basic data munching we need. So we can now create a decision tree, and in scikit-learn, a decision tree where the dependent variable is continuous is a decision tree regressor. And let's start by telling it we just want a total of 4 leaf nodes. We'll see what that means in a moment. And in scikit-learn, you generally call fit, so it looks quite a lot like FastAI, and you pass in your independent variables and your dependent variable. And we can grab those straight from our tabular object training set. There's .x's and .y, and we can do the same thing for validation, just to save us some typing. Okay, questions?
Do you have any thoughts on what data augmentation for tabular data might look like?
I don't have a great sense of data augmentation for tabular data. We'll be seeing later, either in this course or in the next part, drop out and mix up and stuff like that, which they might be able to do that in later layers in the tabular model. Otherwise, I think you need to think about kind of the semantics of the data and think about what are things you could do to change the data without changing the meaning. Sounds like a pretty tricky. Yeah.
Their question, does FastAI distinguish between ordered categories, such as low, medium, high, and unordered categorical variables?
Yes, that was that ordinal thing I told you about before. And all it really does is it ensures that your classes list has a specific order. So then these numbers actually have a specific. And as you'll see, that's actually going to turn out to be pretty important for how we train our random forest. Okay, so we can create a decision tree regressor, we can fit it, and then we can draw it, the FastAI function. And here is the decision tree we just trained. And behind the scenes, this actually used basically the exact process that we described back here, right? So this is where you can try and create your own decision tree implementation if you're interested in stretching yourself. So we're going to use one that's already exists, and the best way to understand what it's done is to look at this diagram from top to bottom. So the first step is it says, okay, the initial model it created is a model with no binary splits at all. Specifically, it's always going to predict the value 10.1 for every single row. Why is that? Well, because this is the simplest possible model, is to take the average of the dependent variable and always predict that. And so this is always should be your pretty much your basic baseline for regression. There are 404,710 rows, options, that we're averaging. And the mean squared error of this incredibly simple model, in which there are no rules at all, no groups at all, just a single average, is 0.48. So then, the next most complex model is to take a single column, coupler system, and a single binary decision is coupler system less than or equal to 0.5. True, there are 360,847 options where it's true, and 43,863 where it's false. And now interestingly, in the false case, you can see that there are no further binary decisions. So this is called a leaf node. It's a node where this is as far as you can get. And so if your coupler system is not less than or equal to 0.5, then the prediction this model makes for your sale price is 9.21. Versus if it's true, it's 10.21. So you can see it's actually found a very big difference here, and that's why it picked this as the first binary split. And so the mean squared error for this section here is 0.12, which is far better than we started out at, 0.48. This group still has 360,000 in it, and so it does another binary split. This time is the year that this piece of equipment made, was it less than or equal to 1991.5? If it was, it's true, then we get a leaf node, and the prediction is 9.97, mean squared error 0.37. If the value is false, we don't have a leaf node, and we have another binary split. And you can see eventually we get down to here, coupler system true, year made false, product size false, mean squared error 0.17. So all of these leaf nodes have MSEs that are smaller than that original baseline model of just taking the mean. So this is how you can grow a decision tree. And we only stop here because we said max leaf nodes is 4. 1, 2, 3, 4. Right? And so if we want to keep training it further, we can just use a higher number. There's actually a very nice library by Terence Parr called dtreeviz, which can show us exactly the same information like so. And so here are the same leaf nodes, 1, 2, 3, 4. And you can see the the chart of how many are there. This is the split, coupler system 0.5. Here are the two groups. You can see the sale price in each of the two groups. And then here's the leaf node. And so then the second split was on year made. And you can see here, something weird's going on with year made. There's a whole bunch of year mades that are 1,000, which is obviously not a sensible year for a bulldozer to be made. So presumably that's some kind of missing value. So when we look at the the picture like this, it can give us some insights about what's going on in our data. And so maybe we should replace those thousands with 1950, because that's obviously a very, very early year for a bulldozer. So we can kind of pick it arbitrarily. It's actually not really going to make any difference to the model that's created, because all we care about is the order, because we're just doing these binary splits. But it'll make it easier to look at, as you can see. Here's our 1950s now, and so now it's much easier to see what's going on in that binary split. So let's now get rid of max leaf nodes and build a bigger decision tree. And then let's just, for the rest of this notebook, create a couple of little functions, one to create the root mean squared error, which is just here, and another one to take a model and some independent dependent variables, predict from the model on the independent variables, and then take the root mean squared error with the dependent variable. So that's going to be our model's root mean squared error. So for this decision tree, in which we didn't have a stopping criteria, so as many leaf nodes as you like, the model's root mean squared error is 0. So we just built the perfect model. So this is great news, right? We built the perfect auction trading system. Well, remember, we actually need to check the validation set. So let's check MRSE with the validation set, and it's worse than 0. So our trading set is 0, our validation set is much worse than 0. Why does that happen? Well, one of the things that a random forest in sklearn can do is it can tell you the number of leaf nodes, number of leaves. There are 341,000. Number of data points, 400,000. So in other words, we have nearly as many leaf nodes as data points. And most of our leaf nodes only have a single thing in, so they're taking an average of a single thing. And clearly this makes no sense at all. So what we should actually do is pick some different stopping criteria, and let's say, okay, if you've got a leaf node with 25 things or less in it, don't split things to create a leaf node with less than 25 things in it. And now if we fit, and we look at the root mean squared error for the validation set, it's going to go down from 0.33 to 0.32. So the training set's got worse, from 0 to 0.248. The validation set's got better, and now we only have 12,000 leaf nodes. So that is much more reasonable. All right, so let's take a 5-minute break, and then we're going to come back and see how we get the best of both worlds. How are we going to get something which has the kind of flexibility to get these, what we're going to get down to 0, but to get really deep trees, but also without overfitting. And the trick will be to use something called bagging. We'll come back and talk about that in 5 minutes.
Okay, so I made it to the hour mark, so I'll be back later. Try to make it to the 1.5 hour mark.
Alright, so I'm back. Looks like my camera is not going to work. I guess this is a better shot of me anyways. So let's get to the 1.5 hour mark on the video.
Okay, so welcome back. So we're going to look at how we can get the best of both worlds, as we discussed. And let's start by having a look at what we're doing with categorical variables. And so you might notice that previously with categorical variables, for example, in filtering, we had to kind of think about how many embedding variables we have, for example. If you've used other modeling tools, you might have experienced things with creating dummy variables, stuff like that. For random forests on the whole, you don't have to. The reason is, as we've seen, all of our categorical variables have been turned into numbers. And so we can perfectly well have decision tree binary decisions which use those particular numbers. Now, the numbers might not be ordered in any interesting way, but if there's a particular level which kind of stands out as being important, it only takes 2 binary splits to split out that level into a single, into a single piece. So generally speaking, I don't normally worry too much about encoding categorical variables in a special way. As I mentioned, I do try to encode ordinal variables by saying what the order of the levels is, because often, as we expect, sizes, for example, medium and small, like not kind of next to each other, and large and extra large next to each other. So it's good to have those as similar numbers. Having said that, you can one hot encode a categorical variable if you want to, using depth dummies and pandas. But there's not a lot of evidence that actually helps. There's actually that has been brought in the paper. And so I would say in general, categorical variables don't worry about it very much, just use what we showed you. Any question?
For ordinal categorical variables, how do you deal with when they have like NA or missing values with that order?
So in FastAI, NA missing values always appear as the first item, always be the 0. And also if you get something in the validation or test set, which is a level that's seen in training, that will be considered to be that missing or NA value as well. All right, so what we're going to do to try and improve our random forest is we're going to use something called bagging. This was developed by a retired Berkeley professor named Leo Bryman in 1994. He did a lot of great work, and perhaps you could argue that most of it happened after he retired. His technical report was called Bagging Predictors, and he described how you could create multiple versions of a predictor, so multiple different models, and you could then aggregate them by averaging over the predictions. And specifically, the way he suggested doing this was to create what he called bootstrap replicates. In other words, randomly select different subsets of your data, train a model on that subset, and store it away as one of your predictors, and then do it again a bunch of times. And so each of these models is trained on a different random subset of your data. And then you, to predict, you predict on all of those different versions of your model and average them. It turns out that adding works really well. So the sequence of steps is basically randomly choose some subset of rows, train a model using that subset, save that model, and then return to step one. Do that a few times, train a few models, and then make a prediction, predict all the models, and that is back. And it's very simple, but it's astonishingly powerful. And the reason why is that each of these models we train, although they are not using all of the data, so they're kind of less accurate than a model that uses all of the data, each of them is, the errors are not correlated, the errors because of using a small subset are not correlated with the errors of the other models, because they're random subsets. And so when you take the average of a bunch of errors which are not correlated with each other, the average of those errors is 0. So therefore, the average of the models should give us an accurate prediction with the work we can predict. So as I said here, it's an amazing result. We can improve the accuracy of nearly any kind of algorithm by training multiple times on different random subsets of data and then averaging the predictions. So then Reinman in 2001 showed a way to do this specifically with decision trees, where not only did he randomly choose a subset of rows for each model, but then for each binary split, he also randomly selected a subset of columns. And this is called the random rows. And it's perhaps the most widely used, most practically important machine learning method, and astonishingly simple. To create a random forest regressor, you use this very lens random forest regressor. If you pass n jobs -1, it will use all the CPU cores you have, as fast as possible. N estimators says how many trees, how many models to train. Max sample says how many rows to use, randomly chosen rows to use in each one. Max features is how many randomly chosen columns to use for each binary split. Min sample sleep is the stopping criteria. So here's a little function that will create a random forest regressor and fit it to some sort of independent variables in the independent variable. So we go to default values and create a random forest, train, and our validation set RMC is 0.23. If we compare that to what we had before, we had 0.32. So dramatically better by using the random forest. So what's happened when we call random forest regressor is it's just using that decision tree builder that we've already seen, but building multiple versions with these different random subsets, and each binary split it does is also randomly selecting the subset columns. And then when we go to prediction, it is averaging the predictions of each of the trees. And as you can see, it's giving a really great result. And one of the amazing things we'll find is that it's going to be hard for us to improve this very much. The kind of the default starting point tends to turn out to be pretty good. The estimator box has lots of information here. One of the things that is this nice picture that shows as you increase the number of estimators, how does the accuracy improve, or error rate improves, for different max features levels. And in general, the more trees you have, the more accurate. It's not going to overfit, right? It's averaging more of these weak models, more of these models in the trained on subsets. So use as many estimators as you like. Really just a case of how much time do you have, and then reach a point where it's not going to be approved anymore. You can actually get at the underlying decision trees in the model, in the random forest model, using estimators underscore. So with a list comprehension, we can call predict on each individual tree. And so here's an array, an NumPy array, containing the predictions for each individual tree, or each row in our data. So if we take the mean across the 0 axis, we'll get that same number. Just remember, that's what a random forest does. It takes the mean of the trees, the predictions. So one cool thing we could do is we could look at the 40 estimators we have and grab the predictions for the first I of those trees and take their mean. And then we can find out what means where they are. So in other words, here's the accuracy. When you just have 1 tree, 3 trees, 3 trees, 4 trees, 5 trees. So you can see. So it's kind of nice, right? You can actually create your own, build your own tools to look inside these things and see what's going on. And so you can see here that as you add more and more trees, the accuracy did indeed keep improving, although the improvement slowed down. The validation set is worse than the training set, and there's a couple of reasons that could happen. The first reason could be because we're overfitting, which is not necessarily a problem, it's just something. Or maybe it's because the fact that we're trying to predict the last 2 weeks is actually a problem, and the last 2 weeks are different to the other options in our data set. Maybe something changed over time. So how do we tell which of those 2 reasons there are? What is the reason that the validation set is worse? We can actually find out using a very clever trick called out of bad error, OOB. And we use OOB error for lots of things. You can grab the OOB error, or you can grab the OOB predictions from the model, the OOB prediction, and you can grab the RMC, and you can find that the OOB RMC is 0.31, which is quite a bit better than the 0.23. So let me explain what OOB error is. What OOB error is we look at each row of the training set, not the validation set, which row of the training set. And we say, so if the row number one, which trees included row number one in the training? And we'll say, okay, let's not use those. Out of those for this training. But we'll just calculate an error for that row using the trees where that row is not included in the training tree. Because remember, every tree is using a subset of data. So we do that every row. We find the prediction using only the trees that were not used, that row is not used. And those are the row predictions. In other words, this is like giving us a validation set as well. But the thing is, it's not with that time offset. It's not looking at the last 2 weeks. It's looking at the whole training set. So this basically tells us how much of the error is due to overfitting versus due to the last couple of weeks. So that's a cool thing. Overfitting error is something that very quickly gives us a sense of how much we're overfitting. And we don't even need a validation set. But is that already there? So that's something to about what's going on in the model. But then there's other things which I can find out from the model. And I've got 5 things that people here which I generally find really interesting. Which is, how confident are we about predictions for some particular prediction entity? Like we can say this is what we think the prediction is, but how confident are we? Is that exactly that, or is it about that, or we really don't know? And then for predicting a particular item, which factors are the most important in that prediction, and how do they influence it? Overall, which columns are making the biggest difference? Which ones could we maybe throw away and it wouldn't matter? Which columns are basically redundant with each other, so we don't really know. And as we vary some column, how does that change them? Those are the 5 things that we're interested in figuring out, and we can do all of those things with random forest. Let's start with the first one. So the first one, we've already seen that we can grab all of the predictions for all the trees and take their mean to get the actual predictions of the model and the RNC. What if instead of saying mean, we do exactly the same thing? Like so. Since there's a standard deviation, this is going to tell us for every row in our data set, how much did the trees vary? And so, if our model really had never seen kind of data like this before, if it was something where there are different trees who give very different predictions, it might give us a sense that maybe this is something that we're not at all confident about. And as you can see, when we look at the standard deviation of the trees prediction, let's just look at the first 5. They vary a lot, 0.2, 0.1, 0.19, 0.3. Okay? So, this is a really interesting, it's not something that we're talking about, I think it's a really interesting approach to kind of figuring out whether we might be cautious about a particular prediction because maybe we're not very confident. There's one thing we can easily do with random forest. The next thing, and this is I think the most important thing in any investment interpretation, is feature importance. Here's what feature importance is. We can call feature importance in a model, it's some independent variables. Let's say grab the first 10. This says these are the 10 most important features in this random forest. These are the things that are the most strongly driving elements for deployment. And so you can see here, there's just a few things that are by far the most important. What year the equipment was made, how big is it? Alpha system, whatever that means, and the product class. And so you can get this by simply looking inside your trained model and grabbing the feature importances attribute. And so here we're making a better calculus, a data frame, and sorting the same amount of importance. So how is this actually being done? It's actually really neat. What scikit-learn does, and Ryan, the vendor of Enterprise, that's right, is that you can go through this tree, and then start at the top of the tree and look at each branch. And at each branch, see what feature was used to split, which binary, which the binary split was based on which column. And then how much better was the model after that split than beforehand. And we basically then say, okay, that column was responsible for that amount of improvement. And so you add that up across all of the splits, across all of the trees for each column. And then you normalize it to level 1. And that's what gives you these numbers, which are the first few of the table and the first 30 of the year. So this is something that's fast, it's easy, and it kind of gives us a good sense of like, well, maybe the stuff that are less than 0.05 is removed. So if we did that, that would leave us with only 21 columns. So let's try it. Let's just say, okay, X's which are important, the X's which are in this list of 1 to keep, retrain our random forest, and have a look at the result. And basically our accuracy is about the same. But we've gone down from 78 columns to 21. So I think this is really important. It's not just about getting the most accurate model, but you want to kind of go fit it as best as possible. And so 21 columns is going to be much easier for us to check for any data issues and understand what's going on. And the accuracy is about the same with the RSC. So I would say, okay, let's do that. Let's just stick with X is important. And so here's this entire set of the 21 features. And you can see it looks now like year made, the product size are the 2 really important things, and then there's a cluster of kind of mainly product-related things that are kind of the next level of importance. One of the trick things here is that we've got like product class desk, model ID, secondary desk, model desk, base model, late model descriptor. They all look like there might be similar ways of saying the same thing. So one thing that can help us to interpret the feature importance better and understand better within the model is to remove redundant features. So one way to do that is to call cluster as cluster columns, which is basically a thin wrapper of stuff that scikit-learn already provides. And what that's going to do is it's going to find pairs of columns which are very similar. You can see here, sale year and sale lapse. See how this line is way out to the right? Well, machine ID and model ID is not at all, it's way out to the left. So that means the sale year and sale lapse are very, very similar. when one is low, the other tends to be low, and vice versa. Here's a group of three, which all seem to be matches. And then product group, test product group, and then F5S space 1 and F5 test. But these all seem like things where maybe we could remove one of each of these pairs, because they're basically pretty much the same. They're one is higher, the other is higher, and vice versa. So let's try removing one of each of these. Now, it takes a little while to train around the forest, and so just to see whether removing something makes it much worse, we could just do a very fast version. So we could just train something where we only have 50,000 rows per tree, train for each tree, and we'll just use 40 reads. And let's then just get the OOB for. And so for that fast, simple version, basic OOB without important x's is 0.872. And here OOB I need. So then let's try going through each of the things we thought we might not need, and try dropping them, and then getting the OOB error for our x's with that one column. So compared to 877, most of them don't seem to hurt very much. Well, that's hurt quite a bit. Right, so for each of those groups, let's see which one of the ones seems to remove it. Here's the 5 back down. Let's remove the whole lot and see what happens. And so the OOB went from 877 to 874. There were hardly anything else. Despite the fact we managed to get rid of 5 variables. So let's create something called x's final, which is the x's important, and drop in those 5. Save them, whatever. Always welcome back again. And then let's check our random forest using those. And again, 0.233, 0.234. So we've got about the same thing, but we've got even less columns. So we're getting a kind of a simpler and simpler model without hurting our accuracy. That's great. So the next thing we said we're interested in learning about is the columns that are, the columns that are most important. What's the relationship between that column and the dependent variable? So for example, what's the relationship between product size and sale price? Well, the first thing I would do would be just to look at history. So one way to do that is with the value counts in pandas, and you can see here different levels of product size. And one thing to note here is actually missing is actually the most common, and then next most is compact and small, and then mainstream. So we can do the same thing for EMA. EMA we can't just leave the basic data, or EMA we actually need this Pandas has built into this for histogram. And that 1950 year we created it. That's kind of this missing value thing, which used to be 1,000. But most of them seem to be well in thousands. So let's now look at something called partial dependence plot. Here is a partial dependence plot of EMA against partial dependence. What does this mean? Well, we should focus on the part where we actually have a reasonable data, so at least relatively 80s around here. And so let's look at this bit here. Basically, what this says is that as EMA increases, the predicted sale price also increases. See, and the log sale price is increasing linearly on another graph. Roughly then, this is actually increasing the relationship between EMA and sale price. Why do we call it a partial dependence? So we're just plotting kind of the year against the average sale price? Well, no, we're not. We can't do that because a lot of other things change from year to year. For example, maybe more recently people can buy bigger bulldozers, or more bulldozers with air conditioning, or more expensive models of bulldozers. And we really want to be able to say, like, no, just what's the impact of the year and nothing else? And if you think about it from kind of an inflation point, you would expect that older bulldozers would be kind of, that the bulldozers would get a constant ratio cheaper the further you go back, is what we see. So what we really want to say is, all other things being equal, what happens if only the year changes? And there's a really cool way we can answer that question with a random forest. But how does EMA impact sale price? All other things being equal. What we can do is we can go to our actual data set and replace every single value in the EMA column with 1950, and then calculate the predicted sale price at every single option, and then take the average of all the options. And that's what gives us this value. And then we can do the same thing for 1, 2, 3, 4. So eventually, the final year will be 2011. So this isolates the effect of only EMA. So it's a kind of a bit of a curious thing to do, but it's a pretty neat trick for trying to kind of pull apart and get this partial dependence and say what might be the impact of just changing EMA. And we can do the same thing for product size. And one of the interesting things we do for product size is we see that the lowest value of predicted sale price, product sale price, is NA. Which is a bit of worrying, because we kind of want to know, well, that means it's really important. The question of whether or not the product size is stable is really important. And that is something that I want to dig into before I actually use this model and find out, well, why is it that something is unstable and what does it mean? Or why is it that that's just important for people? Well, that is the partial dependence part, and it's a really better. So we have looked at 4 of 5 questions we said we wanted to answer at the start of the section. So the last one we want to answer is, we're predicting with a particular row of data what are the most important factors and how do they influence them. This is quite related to the very first thing we saw. Because like I mentioned, you were using this option price model in real life, and something on your tablet, and you went into some option, and you looked up what the predicted option price would be for this lot that's coming up, find out whether it seems like it's been under or overvalued, and then back to overvalued. So one thing we said we'd be interested to know is, well, are we actually confident in our prediction? And then we might be curious to find out, oh, I'm really surprised it's predicting such a high value. Why is it predicting such a high value? So to find the answer to that question, we can use a module called tree interpreter. And tree interpreter, the way it works is that you pass in a single row. Here's the function that's coming up, here's the mole, here's the function year ID, etc. Please predict the value from the random forest of the expected sale price. And then what we can do is we can take that one row there and put it through the first decision tree. And we can see.
Oops, so it looks like I accidentally zoned out and checked my email without even realizing I was still watching this recording. I'm absolutely not taking any of this in. I actually believe I just completely started ignoring the video. The good news is I'm at 1 minute 30, which is my goal. So I'm definitely going to pause it and come back later. All right, welcome back. I'm at the 1.5 hour mark, so we're going to try to get all the way through the video, and then part 2 will be answering the questions. I think it's going to be kind of a rush job again for this one, probably for the other one too, because it's really down and technical into the weeds right now, and as I mentioned before, I'm in the middle of studying for the expert level of something that I actually think will further me along in my career directory right now. So to just all of a sudden change gears, I'm just not sure if there'll be better opportunities for me for having dived into this too much. So I mean, I'm happy to do it. I'm doing it for a reason. I think I'm doing it for a good reason. You know, I just want and the ethics chapter was fantastic. I'm really glad I got a glimpse into that, because there's some really interesting ethical issues going on with social media and AI and recommendations and stuff, and I'm really happy that I went through that. That was fantastic. So just got a little bit more left. It's just going to be 15 minutes because I'm watching it on double speed, and then to do the questions, and then one more week of this, and I'll be done. So all in all, I think I'll be happy that I stuck to it and did it. But I think I would be a little bit more kind of careful in the future to commit to something that was meant to be 8 weeks like this. It's just a lot of weeks. And we actually decided to stretch it out into a 9th week. So I'm glad I participated, but I think it was a little bit much for beginners to this topic. And I think it was a little bit too much of a time commitment to be realistic, especially since we started with probably over 10 people interested, and at the last meetup again, there were only, I think there were 4 this time, but there were definitely more than half the original class has dropped out from it, I think. But yeah, let's get this done. It's just going to be 15 minutes because I'm watching it at double speed, and then I will end this video, upload it as a part 1, and then part 2 will be the questions.
What's the first frequency? And then based on that split, does it end up increasing or decreasing the predicted price compared to that kind of raw baseline model? And then you can do that again for the next split, and the next split, and the next split. So for each split, we see what the increase or decrease in the prediction. That's not right. We see what the increase or decrease in the prediction is here compared to the third. So then you do that for every tree, and then add up the total change in importance by expected. And that allows you to draw something like this. So here's something that's looking at one particular row here, and overall, we start at 0. And so 0 is the initial 10.1. Remember this number 10.1 is the average log sale price of the whole base. We call it price. So we call that 0. Then for this particular row we're looking at, EMA has a negative 4.2 impact on the prediction. And then product size has a positive 0.2. Capital system has a positive 0.046. Model ID has a positive 0.127. And so forth. And so the red ones are negative and the green ones are positive. You can see how they're all going up. So eventually, overall, the prediction is it's going to be negative 0.122 compared to 10.1, which is equal to 9.98. So this kind of plot is what we want to plot. And so basically when we say pre-interpret.predict, it gives us back the prediction, which is the actual number we get from random forest, bias, which is just always this different one, as I said, and then the contributions, which is all of these different values, how important was each factor. And here I use a threshold, which means anything that was less than 0.08 will get thrown into this column. I think this is a really useful kind of thing to have in production, because it can help you answer questions, whether it'll be for the customer or for who's using your model, if they're surprised by some prediction. Why is that prediction? So I'm going to show you something really interesting using some synthetic data. And I want you to really have a think about why this is happening before I pause the video and when I get to that. Let's start by creating some synthetic data, like so. So I'm going to grab 40 values evenly spaced between 0 and 20. And then we're just going to create the y equals x line and add some normally distributed random data. Here's the pattern. We're going to use a random forest here. Now, in this case, we only have one independent variable. Scikit might expect us to have more than one. So we can use unsqueeze PyTorch to add the go from a shape of 40, in other words, a vector with 20 elements, to a shape of 40, 1, in other words, a matrix of 40 rows with one column. So this unsqueeze 1 means add a unit axis here. I don't use unsqueeze very often. I actually go with the index with a special value none. This works in PyTorch and NumPy. Since this way it works is to say, okay, x min, remember that's size the vector of 40. Every row, and then none means insert the unit axis here. So these are two ways of doing the same thing. So this one is a little bit more flexible, so that's why I use more. But now that we've got the shape of this expected, which is a magnitude tensor, an array with dimensions on axes, we can create a random forest, hit it, and let's just use the first 30 bits. Right? So, and then let's do a prediction. Right? So let's plot the original 30 points, and then also plot the prediction. Look what happens on the prediction. Actually, it's kind of nice and accurate. And then suddenly, what happens? This is the bit where you're watching the video. I want you to pause and think, how's this one?
Oh, yeah. Listen to why it's flat.
Remember, random forest is just taking the average of predictions in country trees.
Oh.
Tree, the prediction.
Shoot, I didn't pause in time. It's in double time. Okay, well, I don't know.
It's not the average of the numbers in the leaf node. And remember, we did using a training set trained only the first 30. So none of these are given training set. So the highest we would get would be the average of values within inside the training set. In other words, there's this maximum you can get to. So random forests cannot extrapolate outside of the bounds of the data. And this is going to be a huge problem in time series prediction where there's like an underlying trend. So but really, the more general issue is time data. It's going to be hard for random forests to extrapolate outside the types of data that it's seen in a general sense. So we need to make sure that our validation set contain output domain data. So how do we find output domain data? So we might not even know our test set is distributed in the same way as our training data. But if they're from two different time periods, how do you kind of tell how they vary? Right? Or if it's a table competition, how do you tell if the test set and the training set, the table gives you, have some underlying differences? There's actually a cool trick you can do, which is you can create a column for is valid, which contains 0 for everything in the training set, and 1 for everything in the validation set. And it's concatenating all of the independent variables together. So it's concatenating the independent variables of both the training and validation set. So this is our independent variable. And this becomes our dependent variable. And we're going to create a random forest, not for predicting price, but a random forest that predicts, is this row from the validation set? If the validation set and the training set are from kind of the same distribution, if they're not different, then this random forest will basically have 0 predictive power. If it has any predictive power, then it means that our training and validation set are different. And to find out the source of that difference, we can use feature informers. And so you can see here that the difference between the validation set and the training set is, not surprisingly, so overlaps. So that's the number of days since 1970 or something. So it's basically the date. Well, yes, of course you can predict whether something is on the validation set or the training set rather than the date, because that's actually quite funny. Makes sense. This is interesting, sales ID. So it looks like the sales ID is not some random identifier, but it increases over time. Ditto for machine ID. And then there's some other small ones here that make sense. So I guess for something like model guess, there are certain models that were only made in 80 years, for instance. But you can see these top 3 columns are really true. So then we can say, like, okay, what happens if we look at each one of those columns, those 3, and remove them, and then see how it changes our RMSE on our sales price model on the validation set. We start from 232. And removing sales ID actually makes it a bit better. Well, that's things get worse, machine ID, that's. So we can probably remove sales ID and machine ID, and that means accuracy, and yep, it's actually safe. The most important is going to be more resilient over time, right? Because we're trying to remove the time-related features. Another thing to note is that since it seems that this kind of sale lapse issue that maybe it's making a difference, is maybe looking at the sale year distribution. This is the most of the sales were in the last few years anyway. But what happens if we only include the most recent few years? So let's just include everything else from 2004. So that its X is still good. And if I train on that subset, then my accuracy goes a bit more, 331, 330. So that's interesting, right? We're actually using less data, less rows, getting a slightly better result. It's the more recent data, smaller position. So that's about as long as we can get without random forest. What I will say is this issue of extrapolation would not happen with a neural net, would it? Because a neural net is using kind of the underlying layers of linear layers. And so linear layers can absolutely extrapolate. So the obvious thing to think at this point is, well, maybe with a neural net, we'll do a better job of this. That's going to be next. To this question.
Question first. How does feature importance relate to correlation?
Feature importance doesn't particularly relate to correlation. Correlation is a concept for many models, it's not linear model. So the feature importance is calculated by looking at the improvement in accuracy as you go down each tree and go to each binary tree. We're used to linear regression, and I guess correlation sometimes uses a measure of feature importance, but this is a much more direct version. It's non-linearities and interactions. So it's a much more flexible feature importance. So do the same thing with neural network. I'm going to just copy and paste the same lines of code that I had before. It's not a problem. This is simple. We have the same different columns we had before. Now, as we discussed, for categorical columns, we probably want to use embeddings. For embeddings, we need to know which columns will be treated as categorical variables. And as we discussed, we can use concatenate for that. One of the useful things we can pass that is the maximum cardinality. So max card equals 9,000 means if there's a column with more than 9,000 letters.
Okay, I need a glass of water quick. I'll be right back. Okay, I'm back.
You should treat it as routines. It's not less than 9,000 letters. So that's, it's a simple little function which checks the cardinality and splits them based on the discrete opposite. And of course, it's not actually numerically related discrete. So there's our aspect. And then from there, what we can do is we can say, oh, we're going to be the curve of cell maps. Because actually, cell maps, I think, has less than 9,000 categories, but we definitely don't want to use as a categorical variable. The whole point was to make it that this is something that we can extrapolate. So we certainly, anything that's kind of time dependent, or we think that we might see things outside the range of inputs, in the training data, we should make continuous variables. So let's make cell maps for the continuous neural net and the reader. So here's the number of unique levels decision candidates for everything in our neural net set of categorical variables. And I get a bit nervous when I see these really high numbers. So I don't want to have too many things with like lots of categories. The reason I don't want lots of things with lots of categories is just you're going to take up a lot of parameters. Because in an embedding matrix, this is, every one of these is a row. In this case, I know it's not ID and all of this. It might be just writing something very similar. So I'm trying to find out if I can get rid of one. And an easy way to do that would be to use a random forest. So let's try removing the algorithms. And let's create a random forest. And let's see what happens. And that, it's actually a tiny bit better. So it's certainly not worse. But that's just that we can actually get rid of these ones, one of these variables. So that's it with that one. And so now we can everyone have something before. Now this time we're going to add one more processor, which is normalize. And the reason we need normalize, so normalize is actually by thinking. We didn't need that for random forest, because for random forest we're just looking at less than a gradient, where our binary splits. But all that matters is the order of the assortment. It doesn't matter whether they're super big or super small. But it definitely matters for neural nets, because we have these linear layers. So we don't want to have things with crazy distributions with some super big numbers and super small numbers. So it's always a good idea to normalize things. Neural nets, we can do that tabular neural net by using the normalized alpha. So we can do the same thing before. We can have this tabular object, the neural net, and then we create data loaders and that for the batch size. And this is a large batch size because tabular models don't generally require areas which people ran. It's a convolutional neural net, or NAN or something. Since a regression model, we don't want our range. So let's find the minimum and maximum of that variable. And we can now go ahead and create a tabular learner. But tabular learners can take data models, a wide range. How many activations do you want in each of the many layers? And so we can have as many layers as you want. How many outputs are there? This is a regression of a single output. And what loss function do you want? We can use a lifetime. And then we can go ahead and use one cycle. There's no pre-trained model, obviously, because it's not pre-trained models for industrial equipment options. So we use one cycle. And train for a minute. And then we can check. Our MSC is 0.236. The idea was 0.230. So that's amazing. We actually have straight away a better result than a random forest. It's a little more fussy, it's a bit longer. And as you can see, for interesting data sets like this, we can get some great results with neural nets. But here's something else we could do. The random forest and the neural net, they each have their own pros and cons. There's some things that could happen. So maybe we can get the best of both worlds. And a really easy way to do that is to use ensemble. We've already seen that a random forest is a decision tree ensemble. But now we can put that into an ensemble. We got an ensemble of the random forest. There's also super fancy ways we can do that. A really simple way is to take the sum up the predictions from two models divided by 2 and use that as prediction. that's our ensemble prediction. It's just literally the average of the random forest prediction and the right. And that gives us 0.223, 0.226. So what is that? Well, it's a little hard to say because unfortunately this competition is old enough that we can submit to it and how we refine the table. So we don't really know. So we're relying on our own validation. But it's quite a bit better than even the first place score on testing. So the validation says good job, and this is a good sign that this is a really good model. Which wouldn't necessarily be that surprising because in the last few years, I guess we've learned a lot about building these kinds of models, and we're taking advantage of a lot of the tricks that have appeared in recent years. And maybe this was well, I think it's such a business that both random forests and neurons a lot of alpha, and try both. We talked about the approach from somewhere back, which is where we train lots of models in different subsets of the data. Another approach from solving, particularly on problem trees, is called boosting. And boosting involves training a small model which underfits the data set, maybe like just a very small number of inputs. And then you calculate predictions using a small model, and then you subtract the predictions from that. So these are kind of like errors of your small underfit model. We call them boosting. And then go back to step one. But now, instead of using the original patterns, it's the residence. You train a small model which underfits the data set, attempting to predict the residence. And do that again. You use stopping criteria to just maximum increase. Now, that will leave you with a bunch of models which you don't average, but which you sum, because each one is creating a model that's based on the residual of the previous one. So we subtracted the predictions of each new tree from the residuals of the previous tree. But the residuals get smaller and smaller. And then to make predictions, you just have to do the opposite. Just add them all together. So there's lots of variance to this. You'll see things like GMs, gradient boosted machines, or DBTTs, or gradient boosted decision trees, and there's lots of minor details around some different details. The basic idea is what I've shown.
So question.
All right, let's take the questions.
If dropping features in the model is a way to reduce the complexity of the model and thus remove overfitting, is this better than adding some regularization like weight decay?
I didn't claim root columns were we removed the columns to simplify analyze. It should also mean we don't need to these. There's no particular reason to believe this will regularize, and the idea of regularization doesn't necessarily make sense for enterprises, always.
Is there a good heuristic for picking the number of linear layers in the tabular model?
Not really. Well, there is a number of I guess there are hidden layers what well. No, what I showed. Those numbers I showed are pretty good for a large-ish model. By default, it uses 200 and 100, so maybe start with default, and then go up 500 to 250 if that is an improvement, and just keep doubling them. Main thing to note about boosted models is there's nothing to stop us from. If you add more and more trees, the bagging models around the forest, it's going to get to generalize that effect. So each time you'll use your model as based on subset. By boosting, each model will fit the training set better. So boosting methods do require hyperparameter tuning. You certainly have regularization. They're pretty sensitive. That's why they're not normal. The first go to, they more often make hyperparameter and forest good. They tend to be good at the last thing I'm going to mention is something super neat, which a lot of people don't seem to know exists, which is a shame, it's super cool, which is something from the NP where what they did was they built a neural network, they got the NP embeddings, and then they tried to random forest using the entity embedding as predictors, rather than the approach I described, which is the raw categorical variables. And the error for random forest went from 0.16 to 0.11. Huge improvement. And very simple at the KNN, from 0.29 to 0.11. Basically, all of the methods, when they use NP embeddings, nothing improved a lot. One thing you should try, if you have a look at the further research section of the questionnaire, is asked to try to do this. Actually, take those NP embeddings that you train in neural net and use them in random forest, and then maybe try and some of them and see if you can beat the 0.223. This is a really nice idea. It's like you get all the benefits of boosted decision trees, all of the nice features of NP embeddings. And so this is something that not enough people seem to be playing with. So overall, random forests are nice and easy to train. They're very resilient. They don't require much preprocessing. They train quickly. They don't overfit. They can be a little less accurate. And they can be a bit slow at inference time, because at inference you have to go through every one of those trees. But having said that, the binary tree can be pretty heavily optimal. So it is something you can basically create a perfect high order version of the tree. And they can certainly also be done by parallel. So that's something you can do. Gradient boosting machines are also fast to train on the whole. A little more fussy with hyperparameters, you have to check that. neural nets, many RCS to deal with. They've kind of got the least rules of thumb around, or tutorials around, so you just know how to do it, just to get neural, a little bit less knowledge to do it. But they can give better results in these situations than other approaches, or at least in some improved approaches. So I always start with it, and then see if you can teach it using it. So, yeah, why don't you now see if you can find a table competition with tabular data, whether it's running now, ask one and see if you can repeat this process for that, and see if you can get in the top 10% with a 5 million, even a great stretch goal. If you decision for the algorithm yourself, if it's important, you understand it. And then from there, great.
Wait, he wants us to get in the top 10% of a competition? As just a further research exercise?
Your own kind of parts from scratch. I'm not surprised it's not. And then going and look at the tabular model of the source code. At this point, this is pretty exciting. You should find what all the lines do with the exceptions. And if you don't, dig around and explore, experiment, see what you can do. And with that, we are very excited to say the point where we really dug all the way into the hand of these real, valuable, effective fast AI applications to understand what's going on in the cycle.
What do you expect next week?
Next week, NLP and religion. We'll do the same kind of ideas. We'll delve deep to see what's going on. Thanks, everybody. See you next week.
Okay, so that's the end of part 1. Got a part 2 left where I go through and do all the questions. And then next week will be the last video in the series. Thanks for watching and stay tuned.